Well, hello everyone, welcome back to Zomboland Gaming. I am Zombo Skater, and this is episode number 5? I think it's 5 for Turing Complete. So we are going to go into the last two, I think it's 2 or 3 remaining bits of arithmetic, and then the last 2 bits of memory. Yeah, so it's 3 of arithmetic and then 2 of memory. So we've covered quite a bit, and I want to start off today with 2 comments that I've gotten on some of the videos. They're actually really good comments. One slightly trollish, but I got what you were trying to get me to do, so I approve and agree of the comment, and we'll get into that. But first, one of the commenters, David Alexander, mentioned, and I was going to do this originally, but then for some reason I just decided to make this an expanded version of it. I think just to show something, but I wanted to show what his comment was. So here was our the original bigger OR gates and bigger AND gates. So we basically had the middle input going to both gates, so it's A or B, and then B or C, and then the AB combination, BC combination then goes to another OR gate. Obviously that works. However, we can do that much simplified, save ourselves a logic gate, and David Alexander reminded me of it here. Same exact thing. It's A and B, or sorry, A or B. I should be using the right terms here. A or B, and then that combination of A or B OR'd with C. Still works the exact same way. We can tick straight through it, and you can see exactly why it still works. Relieves us of one logic gate, so it makes the circuit smaller. Perfect comment. I like stuff like that. Shows a way that we can make a circuit a whole lot smaller, more efficient than what it is. And the same thing applies for the AND gate. All we're doing here is A and B ANDed with C. So you got the A and B combination, both have to be on in order to get the output on, and then the AB combination ANDed with C, so all 3 of them would had to be on to come out. And we can see this if we step through it all the way real fast. Bam, there you go. That was probably a little fast, but so you get the point. The next comment, and you'll probably see it up on the screen here, by a person named CR. Don't know anything else about him. I like the comment that you are making me aware that I'm using terms that aren't quite correct. And while this is a video game that doesn't base a lot of itself in reality, as we can see through some of these components we've gone through, so really using correct terms isn't that much of an importance. But, however, you are right. So I am trying to show the difference between the real world versus what they're doing inside this video game. I also play Minecraft, and I do a lot of redstone Minecraft things, and everything in that game has to do with game ticks or clock ticks. So the term I use, clock ticks, while it can work, is not the correct term, and he is absolutely right. I should be using states. It is the state of that logic gate, especially once we start getting into, if they do, I don't know if they do here, but like JK flip-flops and things like that. Definitely using the state is the appropriate term I should be using for whatever step that the logic gate is in. You know, it's either in a, you know, whatever state that it would be in, right? You know, is this thing turned on, turned off? We moving to the next state where the output is then turned on or off, so on and so forth. So should have probably worded your comment a little bit nicer there, guy, but I very much highly approve of what you were trying to show me there, and thank you for correcting me and making sure I'm trying to use appropriate terms. I'm probably still going to use clock ticks just because I do so much more with redstone logic, and I'm not a damn logic engineer, logistician, computer architecture engineer, whatever you want to say. So, all right, let's go ahead and get on in the video. That was enough jibber jabbering on about comments. Thank you very much, by the way, for all the comments. There were some really great comments. Really glad to see that I'm not the only one struggling with some of these things. Also really glad to see people coming up with such amazing solutions and ways to do this really better. It's pretty fun. I'm having a lot of fun with this. So first one we're going to get into is Demux. Right away, we're going to get into my frustration of how this game doesn't allow us to do real world things. But Demux, or multiplexer. That's the multiplexer is really what mux means, right? So demultiplexer in a real world scenario, simplistically what it is, you have a certain number of inputs coming in, and then you basically will double the amount of outputs out. What these are really used for is like addressing, just because you can take, you know, if you have 2 inputs then you can have this one be on or off, and you can have this one be on or off. And then the combination there is going to have 4 combinations of that coming out, right? If we were to look at a truth table, the way that they get you to do this in the game, the most simplified way to do this in the game is not how I would do it in real world. I'm going to show you what I did in the game, and then I'm going to show you the example that actually happens to work in the game as well. So here we go. Create a component that can switch a signal between 2 pins. Right away, we already know of a component they've given us that will swap between 2 pins, and that is the SR NOR latch. If you have one on and the other one is knotted, so it'd be off, then you're going to have, set or reset. You're going to have your Q not or your Q on, one of the two, right? And then when you input the other direction, so when this turns off, this turns on, it basically resets it and swaps it back. And we've seen that before. You can see from the truth table down here at the bottom, if the input's on or off, we want the output 1 to be turned on, the output 2 to be turned off. And if the input is turned on, we want the output 1 to be off and the input 2 to be on. So it swaps, right? So if we look at this SR NOR latch here, you can see down at the bottom, if you have, in this case, 2 inputs, right? So if you have them both off, doesn't really give a shit about it. If you have input 1 on, input 2 off, then you're going to have A turned on, and then what they call opposite of A, or A prime, A naught, whatever you want to call it. I call them Q and Q naught just because I'm used to dealing with JK flip-flops, and that's the output terms. So A would be turned off, and the opposite would be turned on. If we turn input 2 on, A turns on, the other turns off. So we already see right here, just this middle section of our truth table, it holds true. So since we only have one input, all we're going to do is just come off the line here and not the other side. And we've seen ourselves do this in other levels here. And so what's going to happen is whenever this line turns on, the NOT gate will turn the other side off. So if we tick on through it, you can see, there we go. We're off, so our NOT gate turns on, and we get our A out. You go the opposite direction, you can see that now we have this turned on, the NOT gate turns off, and now we flip-flopped over, bam, coming out. So that's all they want to get us to do here. So I'm going to show you what a real demultiplexer looks like. So in a real-world demultiplexer, your in, like I said, is used as addressing, right? Normally you would have more than just one in, but in the case of this, just think of this as the NOT gate would be like second input, and then this one would be the regular input. So all we're doing is we're going to take them to 2 separate AND gates. Think of these as enable lines. So they're addressing directly to which one of these AND gates has the potential to even work at all. Because with this input being turned on, one of these is going to give an off signal to the NAND gate, which means that it won't be working no matter what the other side is. And then the on line here can be either used as like an enable or the actual data that you're wanting to send through. So in the case of this, when this turns on, both of these AND gates will feel this data, but it takes the addressing of the actual input to turn one of these AND gates on. So if we step it through, you can see I've got nothing turned on, which means my NOT gate turns on. And then this AND gate has this other side of the data signal, and boom, we got an output out. If I flip-flop it the other direction, you can see that data line is still going to both AND gates, but now we're actually turned on, so my NOT gate turns off, and now the other side turns on. Another way we could do this is with a component that they give us in-game, the switch. Same thing with the switch. The switch is almost like an AND gate, essentially, but this will allow us, the AND gate's only letting us do bits. The switch is letting us do bytes. So if this was a byte input, then we could actually push a byte through here and not just a bit, but would work the exact same way. And you can actually see the number 1 coming down there, which is kind of nice. So that's a demultiplexer. So this is a more representative of a real-world multiplex or demultiplexer. A multiplexer, by the way, is just the opposite of a demultiplexer. So instead of like 2 coming in and one input coming in and 2 inputs coming out, you would have 2 inputs coming in and 1 input coming out would be a multiplexer. Yoink, go away. I hope that makes sense. All right, so now we're moving on to a bigger demultiplexer. So all we're going to do is that AND gate circuit that I had from the last one, the actual real world version of a demultiplexer. And all we're doing is we're going to make it bigger. So let's see down here. If we go, no, not to that. Let's go back to the words that he was using. So we want a thing like the other thing, but just a bit bigger. With 3 bits of input, there are 8 combinations. Make a circuit that selects 1 output for each of the 8 combinations. No more or less than the 1 bit should be at a time. So fortunately, up here in our gates, we have a 3 input AND gate. We have 3 inputs. So all we're going to do is, if we look at our truth table, we're just going to make 8 AND gates, because we know that they told us that with 3 inputs, we have 8 combinations. So we already know that we can just use 8 AND gates to come down here. And then if we look at our truth table, all you're going to do is anywhere that there's an off signal, so something red, put a NOT gate. So in the first case of the first state here, we've got input 1 is off, input 2 is off, input 3 is off. So this first AND gate has all of our lines coming in into NOT gates. Second state here, we've got input 1 is on, so it's just going to go straight into the AND gate, but input 2 and 3 are off, so we'll have 2 NOT gates. And you're just going to do that the whole way down to where we get to the 8th state here, and it's going to be everything is turned on, so everything just goes straight into the AND gate. And then the way that they have these little outputs here is it's 1, 2, 3, 4, top to bottom. 1, 2, 3, 4, bottom. So we can just think of these as 1, 2, 3, 4, and then the next ones are 5, 6, 7, 8, even though it's just individual component. They haven't given us an 8-bit thing, even though they did right here. I mean, we have a bit maker. I don't know why they just didn't use this. I don't know why. So anyway, so if we step this through, you can see when nothing is turned on, all 3 of these NOT gates are turned on, so we get an AND gate out. Next step down, you can see only our A is turned on, so our input 1 is turned on. So this AND gate is now feeling these 2 NOT gates and the AND gate, so on and so forth, and just steps all the way through individually. So that's just a bigger version of what we made in the last circuit. We had our intern add a disable bit to this component. We were tired of looking at him running in circles, and we're looking for other pointless and tedious tasks to give him. You were definitely giving me pointless and tedious tasks sometimes, my guy. All right, moving on. Okay, the last bit of arithmetic, 1 way. Oh, this frustrates me. Oh, you know what? Let me actually show you something. So speaking of demuxers, nope, that's an octobus transceiver. I didn't do it. I did not bring it up. Actually I can. Let's go ahead and 74 HC was a 139, 139. Yeah, right here. Does this have the actual? Nope, it doesn't. No, go away. Go away. I don't want this. Data sheet. We should be able to pull up a picture of showing this. Go faster, computer. Oh my god, my internet sucks today. Are we gonna show it to you? Come on, PDF. Good lord. Apparently I'm having a crappy internet day today. Normally I don't have crappy internet, but today of all days when I want to record, go figure. All right, here we go. Right here. So I don't know if I've shown you guys any of these schematics, but you can look them up for everything. But so basically what we're doing here is this is a 2 to 4 line decoder / demultiplexer. So what it is it's 2 lines coming in, 4 lines coming out, just like we talked about. And if we look down here at the schematic here, this E is our data line, or sometimes you can think of it as an enable line, because we're not sending bytes through this like the game is showing. It's an individual bit, so the data line is going to be a 1 or a 0. So I like to think of them as an enable line just because it makes more sense to my brain. Plus, it's got the letter E. But essentially, it's a data line, right? So this would be the data that I'm wanting to push through the gates, whereas the A0 and the A1 actually is an address line. So if we follow this through, you can see the reason they have these inverters here is just because it's showing you that internally, some cases, sometimes you'll see them on the schematics here. They'll put a little dot showing you that it's the opposite, an inverted input or an inverted output. So all they're doing here is showing me that I've got an inverted input. So if A0 is turned on, you actually have a 0 coming to this point right here. So then coming to this NAND gate would be a 0. And then coming across this inverter, we swap back over to 1 again, which is coming into the NAND gate. So just opposite of what I drew on my schematic. On my schematic, I have it just being the normal input coming in. So if it's a 1, it's a 1. If it's a 0, it's a 0. And then I have it going to an AND gate instead of a NAND gate. So we're just opposite, basically. And then it's just showing you that, once again, the output is inverted. So the output of the NAND gate gets inverted again and then gets inverted again to get your output. So it's a little bit of a weird way to do it, but it still works out the exact same way that we have done it. And we could prove that with a truth table. But these are really great because they actually bring down a function table, and you can see like any kind of current limits or any of that kind of stuff that concerns as you're using these chips. But this is a real world version of what we just built in the other thing. And I probably shouldn't have closed that out because I needed the other one. Anyway, so what we're moving on to here is called one way, right? So what they really want us to use here is an octal bus transceiver. Or not an octal bus transceiver, a bus transceiver, which I believe is 74HC. Crap, I can't remember. 74 series octal bus transceiver. I cannot transceiver? Is that how you spell Seaver? Data sheet. Here we go, right here. So this is what they're trying to get us to do in this thing. But one, they don't let us use circular dependencies, right? We've already seen that they will not allow circuits to flow back into each other, which it is doing in here. Plus, we don't have tri-state buffers. That is something we're not going to get into because they do not have tri-state buffers in this game. You can sort of think of tri-state buffers as an AND gate. Doesn't quite work the same way, but it does. If you're playing Minecraft, anytime you would encounter a tri-state buffer in real life, just use an AND gate and it works. But essentially what this is doing is, say you have a bus, right? You've got 8 bits coming from one way, 8 bits coming from another. Say like, here's your bus work, and here's the output of your ALU or your memory circuit or your program counter or whatever, right? Well, there's times that you do not want to allow the program counter to come out to the bus because your bus is sending information to the memory or to the ALU or your register A. You don't want to mix and match the register A and B memory together. So these are handy for making sure that whatever component you want the bus to go to will only flow to that component. And anytime you want nothing coming from the bus, but you want something from a component to go to the bus, you only want it to go from component to bus, right? So what this is essentially you've got a direction, which the direction is just going to tell you, am I coming from the bus to this side or from this side to the bus? And then the OE is the operation enable. So that's saying, okay, go ahead. You can actually send the information one way or the other. And then these tri-state buffers are basically acting like a pass-through, right? So it's saying you go this way, and now you're on the input of the B side coming from A. You coming from B, you can go out the A side, right? And you can kind of see that here. So this direction is enabling this A side. The operation enable is going right here to enable the B side coming through, right? So that's what this is doing. And I have a version of this in here, but this game actually kind of makes it so much more simple. And that was a really long, lengthy explanation. I'm really sorry about that. I couldn't help myself. But basically, let's read what they want us to say. This level starts with 2 special components. They simultaneously act as an input and an output. So they've got 2 things here, and you can kind of see it on either side of the screen. They're going to go input or output. It doesn't matter. They will go both ways. Make sure the signal flows only from the left to the right. So we're not even worried about the signal going right to left. We don't have to worry about that. All we care about is going from the left side of our screen to the right side of our screen. So test 1, both sides will be off. So no information is flowing at all. Test 2, the left side should turn on and the right side should also be on because we're going to flow that information from left to right. Test 3, the right side's going to turn on, but we want to make sure that that flow does not go over to the left side. So we have to make sure that the left side stays off. We already have a component for this, and we've talked about it before. If we come up to our miscellaneous, not miscellaneous, where's that at? Switches right here, bytes. We can see this right here. If I click on it, you can see that you got an enable, it's got an input, it's got an output. It will not allow an output to act as an input. It will only flow information through from one side, and it's conveniently from left to right. So that's all they're wanting us to do here, is we've got, if this turns on and we have an enable, boom, the switch allows information to go that way. If the enable is turned on and this side is turned on, it doesn't matter. It's going to the output, and it won't let stuff go back this way. So we can see this here. So switch is turned on, test 1, right? Switch is turned on, but we got nothing information, so nothing flows. Switch turns on, Now we've turned on the left side, boom, we've got an output, and you can see that 1 flowing in. Now if we turn the other side on, but we leave the left side off, the switch won't allow that to go back in. So that's pretty simplistic. There's certain times in this game actually, like, you know, helps make sense. Like, it wants me to flow information left to right. Boom, a switch, got it. So I actually drew up, I believe this should be, yeah, right here. So this is kind of that representation of the, one of these would be the directional control, and the other one of these would be the operation enable. And then all it's doing is going to one side of an AND gate as either I'm going to allow you to go from A to B, or I'm going to allow you to go from B to A. But they don't allow circular dependencies, so this doesn't work in game. But that's essentially exactly what we just saw in the schematic online. But instead of tri-state buffers, I'm using AND gates. I could probably have also represented this with switches. The switches would have been a little bit more realistic to tri-state buffers, but you get the idea, right? It doesn't work in game because of circular dependency. All right, so that is arithmetic done. We only have 2 bits left in memory, and then we get into CPU architecture. Nice. All right, so little box. This one kind of frustrated me, and I wrote myself a little bit of notes, and I want to make sure that I remember what I wanted to talk about here. Can you fit 4 bytes of memory in this limited space? In this level, you have to build a circuit that can save and load. We've already seen that kind of stuff, right? We can either use an SR NOR latch as a save and load, because that was examples that we've given before. We can use a demultiplexer, because that will also allow us to have addressing. We've got all these different components we've learned so far. We just have to make sure we can cram it in. You were given 1 bit that determines if you were loading, another bit determines if you were to save. So it's just got an input. You got an input that just has the 2 lines coming off, which we have seen before in another one of our levels, where one's on, one's off, and it just swaps between the 2, right? And that's what we went to an SR NOR latch before. And it comes with a corresponding value. Additionally, you have 2 address bits. So that's going to be our demultiplexer, an A0 and an A1. With 2 bits, there are 4 combinations, 1 for each bit of memory in this level, as we discussed in the demultiplexer. And then these tips, don't worry about them. Join wires in the middle and use right angles, or this will be a mess. Spacebar rotates components. So somebody actually, I can't remember who mentioned the comment in a couple videos ago, and I had mentioned it. I think I might have mentioned it in passing. But if we take any kind of gate, right? If I put this gate down here, we can actually hit spacebar and we can rotate the gates. So if I haven't mentioned that before, and I'm sorry, I don't remember which commenter said that, there you go. You can actually rotate all of these things. But here is the messy circuit that I have made. I really wish that they gave us like flip-flops, like JK flip-flops and D flip-flops, or any kind of toggle flip-flop or any of that sort of stuff. It would have made this a whole lot easier, because I don't need this giant mess of crap in order to make a registry circuit. It's so much easier to make an actual register that reads and writes with addressing than this. But utilizing what they gave us, they said that we're going to have 1 in bit, which is this where the yellow lines are, right? One side is going to be our save, and I don't remember off the top of my head. Okay, yeah, so the right side of this bit is going to be my loading, and the left side of this bit is going to be my saving. So all I've done here is I've taken, and I know it's difficult to see here, but if we follow this down, you'll see it swaps over to different colors, and all I did there was to show which register it's going to. But this load is going to the middle pin of every single one of these switches right here. So these 4 switches on the right side are my load enables. I'm enabling these to load. The ones here in the middle are all my save enables. So these 4 switches are going to a specific register, which is this bit right here. So if you see here, oh, sorry, did I mention that wrong? Oh, sorry, this switch is actually going to the top line. I was looking at the actual input of the switch. Sorry, the rightmost switch is going to the top of this register bit, which is load. The left switch is going to the middle of the register, which is my save. And then the bottom one is the actual value to save. So then what I have down here at the bottom is these 4 switches that are coming from this data line right here. And the data line is going to all 4 of these switches. And then the output of this demultiplexer is what's selecting which one of any of these switches to let me know that, okay, this piece of data can come from this switch, which is going into register 1. If I have the save or the load on for register 1, I'm going to save or load that data. The part that I had a little bit of frustration with this was I can't remember how I did my circuit originally. I think I had a hell of a lot of AND gates. I mean, it was just a disastrous mess. And I could get it to save an output, but the moment that it wanted me to recall information from a register, the register information was gone. It was deleted. I wasn't saving into each register, which is why I went to the switches. And so where the switches are specifically saving and loading and enabling the data coming in. And so the demultiplexer we just saw in the other schematics before, it's just turned on its side instead. And then we're just taking these lines out, and it doesn't look like it's going 3 ways, but it is. You've got this enable coming down here to this bottom switch. It comes across this line to the switch for the save, and then comes across this line right here to the switch for the load. So if we step it on through, in this case, it wants us to save 94. This is another thing that frustrates me. I'm looking at a decimal number. Internally, what you don't see is the actual 8 bits, of data coming in that would add up to 94 in binary, but they're giving you a decimal. This isn't how we would do things in real world. You're not going to send, if you had serial transmission, it would take 8 clock ticks, 8 pulses of the clock on either a leading or falling edge of the clock circuit to make that bit of information get stored somewhere. The next one comes behind it, gets stored somewhere. The next one comes behind, gets stored somewhere. And then once all those 8 signals have reached whatever component it's going to, they then would come back out as individual bits, like in a shift register or something like that, and then form the number you want. We're not sending all 8 all at one time. Even parallel transmission, right? You still have 8 individual lines that each have a bit of information that then get utilized. So looking at it like this sometimes just makes my brain hurt, which is also where I had the frustration with this. So I had to make sure I couldn't use AND gates, right? Because if I'm using AND gates, that's only outputting a 1 or a 0. I need to output the actual byte piece of information, which is why switches work, because the switch is letting the byte information go through. So anyway, getting back to this, right? So they want to expect to see A0, which is this bottom register here, having a 94. We've got our save line turned on. We've got our data enable for register 1 turned on, and our load line is not turned on. We're storing that information. Cool. Let's go on to the next tick. Look, that's another reason why I said clock tick, because it actually says tick up top. So if we do that, now it wants us to, it says output the 94, right? So now our save is turned off because that register has that information stored in it. We turn on our load line, and then we actually have our load coming out. Boom, we got 94 coming out. So now our save hasn't changed. We still have this information saved in here. We just stopped loading it. But now it wants us to take this 47, and it wants it to output into a B0. So it's calling this second one up here B0. I would have called it A2, or, and then B1 would have been A3 in my opinion, but whatever. So they're basically A register and B register. I think they're setting us up for actually an ALU in this thing here, because you'd have an A register, which would be A0 and A1, B register, which is B0 and B1, and then you take your 2 registers and you could use those 2 bits of information to add or subtract. But that's getting ahead of us. So, okay, we've now basically save enabled this line up here for B0. We are enabling right through here, coming into switch right here, the second one down, boom, coming up, and now we have our 47 stored. And you can see our 94 is still stored. We tick it over because it wants us to output that 47, and bam, we have 47 out. See, that 94 is not being loaded and or saved, so the 94 just doesn't give a crap. It's just inside that register, and our 47 is coming out. Moves on to 145, same thing, right? Outputs 145, moves on to 177. Now, all of our registers are full at this point, right? And this was the point that I got to before, where I hadn't paid attention, and I was using a whole bunch of AND gates and stuff, and all of my registers were zeroed out except for the current one that I was on. But right now we have 4 registers full of information. So if we output that 177, now we go to the next part. It wants us to load, does it want us to load 231? No. So it's got 231 bits of information coming here, but it wants us to load the 145, right? So we've got basically register number 3 or A1. A1 is turned on right here. So that's where we're addressing to. But we don't have our load or our, we don't have our save turned on. So none of the saves are turned on. So this bit of 231, which is actually coming here to A1's register, doesn't matter because we're not being told to save that information because our save line is turned off. So we're just going to load what's currently stored in there out. And now you can see, now we're going to overwrite the information in A0. So we've addressed to A0, which is the orange line. We're allowing this 226 to come over. And now our save line is re-enabled, enabling this switch to allow 226 to be stored into that register. So there we go. That's how that works. So hopefully that was not as confusing as I probably just made it out to be. Essentially, we have 3 separate enable lines enabling load, save, and the data. And then we have a demultiplexer for the addressing of which register we're going to go to. In our advanced civilization, forcing prisoners to do extremely menial tasks is slavery and is technically illegal. That is why we instead had our intern create the 256-byte version of your component. So they're going to give us a register now. Cool. Yeah, see, there we go. RAM, a bit of memory. All right, on to the last one. And this one was the most frustrating for me. Counting is so fundamental, even insects do it. From counting, species can evolve to compare and do arithmetic. Arithmetic. Wow, words. And before you know it, you have an apes building computers. Make a device that counts increments once per tick. Build a counter that will increase by 1 each tick. Additionally, there should be an option for overriding the counter with a given value. You are given 2 inputs and a bit and a byte. The bit input should toggle between counting and overriding with the value of the byte. So if we had JK flip-flops available to us, we could make a perfect counter. 4 JK flip-flops, we'd be good to go. We could make a counter. If we wanted to, we could have an override enable that would take a binary, 4-bit and overwrite the number, or an 8-bit, depending on how big we wanted this, right? But we don't have JK flip-flops. We also don't have AND gates or OR gates that allow bytes to pass through. So you really have to think about what components they give us in all of these components up here that allow bytes and or bits to come through. So if we come up here back to what they were telling us to do, right? So build a counter, which will then increase by each tick. Well, we kind of already know that an adder will add up, right? And because they give us right here under bytes, they give us a byte adder. Cool. We can actually add bytes. So I'm going to go ahead and use this, right? Because I want to make sure that it's going to give me more than just 0 and a 1 or a carryover of 0 and 1, right? So I'm going to use this byte adder up here. I'm putting this on signal in here to permanently put a 1 into this. And then what we're going to have is, as we have our input here, this will give a signal of 1. So this is going to enable these 2 switches. So this in, which they said, the bit input should toggle between counting and overriding. So we're using this here as a inverted signal and a regular signal. So that way, if it's turned on, then we'll have our overwrite, which is this byte of information coming here. And then it will, so if we're turned on, it will overwrite because the NOT gate will turn to 0 and will make this switch not work. But if we flip-flop it and we turn this off, we won't be overwriting any information, but now this NOT gate inverts to a 1. We enable this switch, which will allow these to come around and over. So because we're using bytes, we also won't just be 1, 0, 1, 0, 1, 0, like that with a carryover, and the carryover having to go to another adder. We can just take an actual byte of information and keep adding 1 to it, because this on is going to be just a 1 or a 0. So we're always going to take whatever this bit coming out of this register here. We're just going to take this, and it's a byte register. Then we'll come up here and add to that byte, right? So a little bit of confusion here, but it should make sense once we step it through. So you can see right now that we've got the input is turned off. So this switch is disabled. So this 218 won't be coming through because the switch isn't allowed. Our inverter inverts the signal, making this switch enabled. So if we take this on signal, which is permanently on, and it's permanently loading and saving into this register. Let me see if I can, right here. So you can see load and save are both permanently held at whatever the on signal is. So this is going to basically just, I want this information, put this information out. So once we turn this on, let me reset this. Boom, like this. So you can see that the load and save are turned on. We've got our 1 coming from our adder because we have 0 coming in from our information line. So 1 plus 0 makes 1. 1 comes back down through the switch, gets stored into our register. So we've added 1. We go to the next tick. Now we already have a 1 stored in this register. The 1 gets loaded out, comes into the adder, 1 plus 1, and a byte adder will make 2. In a regular adder, it would be a 0 out with a 1 carryover, but this is a byte adder, so it's 2. So 2 now comes down through the switch because the switch is still enabled, getting stored in the register. Next tick, we're going to add another 1. Same exact thing happens. The 2 comes out of the register, adds with the 1 from the on signal, gets a 3. 3 comes through the switch. 3 gets stored in the register. But we're actually outputting 2 because the 2 was what, the 2 is what came out. So initially 2 comes out, which is why I don't understand why circular dependency is not working here, because technically this is kind of circular dependency. This register is depending on the output of the adder. Beyond me. All right, what I really want to do is I want to get up to where they, let's reset that. Bam, and right here. So now we're getting into overriding. So our input now is turned on, which means our switch is disabled, which means we're not taking anything from the adder back into the register. Instead, what we're doing is we're enabling this byte of data down here to come through, and the 108 goes and gets stored up in the register. And then now we're going to overwrite that 108 with the 79. So the 108 just gets pushed straight out of the register to the output, but this 79 is enabled coming up into this register. We're not adding, once again, we're not adding the 109 up into here because that switch isn't enabled. We're just overwriting that information in the register with 79. But now we're going to add 1 to that 79. So we've turned off our input, which enables the switch for adding, but disables the switch for overwriting. So the 79 gets pushed out of the register, adds with the 1 from the current on signal. 1 plus 79 makes 80. 80 comes through the switch that's enabled. It gets written to the register, and the 79 that was there originally is pushed to the output. I hope that makes sense. I really, let's see. Let's go back to the to here, and let's see if we can't pull up a good schematic. I don't think I have a 74 series counter. I want to show you guys. Do we have any? Data sheet. I don't know which one is a good counter number. 191. Let's see. This might work. You have an actual data sheet for this? No, you don't. 74 LS 191 data sheet. I'll just erase all this crap. Bam. Hopefully this will help make sense. Okay. So if we go down to the schematic, here we go. So you can see this ginormous thing. So this is basically a what is an 8-bit? Yeah, it's an 8-bit counter, right? And this has got some other stuff to it, but essentially you have a clock pulse that's acting as an enable. You have your up or down counter, and you have all these data inputs. The data inputs would be essentially like our overwriting. Otherwise, it'd be acting as a counter, and then the load would load our data bits. So you've got a load line coming down here, which, as we've seen with demultiplexers and some of the other circuits, the up-down counter, the clock pulse. I'm not sure what C10 is. C10 looks like it is powering. So this is another enable, and it's enable for count enable is most likely what it's doing, because it's basically this JK flip-flop circuit over here. It's keeping both the J and the K on at the same time. And as we'll get to in one of my digital theory episodes, we will be getting to JK flip-flops. We'll also discuss them in the Minecraft Redstone. Probably not going to be discussed inside this game because they require circular dependency. But if you actually have both the J and the K, you can also think of these as the S and the R, the set and the reset off the SR NOR latch. If they're both turned on, your JK flip-flop will just constantly toggle. As long as they're both turned on, your JK flip-flop will just constantly go Q on, Q not off, Q not off, or Q off, Q not on. And they'll just keep toggling back and forth, which makes a perfect counter. And what they're doing here is they're taking the Q output out, but then they're taking the Q not coming back in to an AND gate to then give you a carryover, which will then be re-added back in. So that's what an actual counter looks like. Very messy, very different from what we're doing. But once again, it's using individual bits of data, not bytes of data, which is where I think this game kind of fails, because we could. There's no reason why we shouldn't be able to have circular dependency in this game. But so there you go. So hopefully that made some semblance of sense. Utilizing what's in game, bits and bytes, to make something work instead of just having just bits. I really wish they would just require just bits and allow us to make actual circuits using circular dependency and individual bits like we would in real world. So anyway, I think that pretty much covers all of it. Run all the way through it. Bam, there we go. Onwards. Whew, so we are now done with arithmetic, memory, and all the basic logic. I know that probably was a little bit more of a lengthy explanation on some of these things. I probably ended up confusing you even more, but you at least got to look at the circuits that make the levels work. If you have any questions or want me to try and explain things in a little bit better terms, very much put that in the comments. And next week, we're going to get up into this. I'm excited. Look at this working computer. Oh, we're so close to having an actual working computer inside a computer game that's being played on a computer. Computerception. Anyway, hope you guys enjoyed. I'll see you guys in the next episode. Most likely Satisfactory coming out on Wednesday, Minecraft coming out on Friday, and then we'll have either a digital theory class, which I've got the next one written up. I just need all the pictures and stuff to go along with it. And then, or we'll have another episode of this coming up on the Saturday following as well. So thanks everyone for watching. Don't forget to like, subscribe, comment, all that doohickey stuff that everybody requires. And I'll see you guys in the next episode. Ta-ta for now. Bye.